Okay, good morning, everyone. Welcome back and welcome to the last week of classes. Obviously, since we're reaching the end of the semester, a couple housekeeping notes about the final project before we get back to the last bit of lecture material. Today we're going to just talk about Interim Video 3, which is the third and final interim video. As the name implies, these are interim or increments towards your final project, which you're demonstrating to us as usual in video form. Interim Video 3 is due at 11:59 p.m. next Monday as usual, which is the night before our final project presentations, which will start, again, this was not my choice, we're going to start very early on Tuesday morning at 7:30 a.m. We will talk about interim video today. We will talk about what you're doing on Tuesday, the oral presentation and the submission of the written report. We'll talk about that on Thursday. Okay, so you've probably seen this already, but just as a refresher, in the final project document, in Interim Video 3, in Interim Video 1, you showed us the very beginnings of the additional functionality that you're going to be adding to your system. We took a pause in Video 2, and you were adding a visualization to this. Normally, you would have been doing some user testing this past week. In Interim Video 3, you're returning and you're showing us the almost complete implementation of your functionality. So, for example, if you're doing the math game, what you might have shown in Interim Video 1 is just the ability to flash up simple equations with a question mark indicating which digit the user should sign. In Interim Video 3, you might want to show that you've now implemented that math functionality almost completely. For example, you might show that your system now switches from displaying single digits when the user is just beginning to learn ASL. It will switch to equations as a function of the skill of the user. As they get better, you'll switch from teaching ASL to teaching math. For example, if they sign 10 digits in a row correctly in under 3 seconds, this is a typo, if they get 10 in a row correctly for each of 3-second presentations, so over a span of 30 seconds, they get 10 out of 10 correct, the system switches to math. If they fall below some performance threshold as they're in the math segment of your game, it switches back to single digits. Yeah, so you're showing a dynamic increase and decrease in the difficulty of whatever your functionality is. Okay. For the graduate students, you're adding in some additional functionality that is triggered by the user using their secondary hand. This past week in Interim Video 2, you should have, the grad students or students that are taking the class for graduate credit, you should have included an additional video showing one function triggered by the secondary hand, like a closed fist triggering fast forward to the next lesson. I want to go faster. In this interim video, you might show 2 different functions triggered by 2 different gestures with the secondary hand. All good? Any questions about that? Okay, as promised, we will talk about the oral presentation and the written report on Thursday morning. All good? Okay. All right, so back to our final segment of the course, this idea of looking inward, and there's sort of 2 interpretations of looking inward. We as a society are becoming increasingly immersed in video games and virtual reality. We are entering virtuality. And at the same time, our technologies are also interpenetrating us in the literal sense when it comes to cyborg technologies. We're going to talk in lecture 26 and 27 about wearable technologies, which sit on the skin, and then cyborg technologies, which sit under the skin. We're a little bit behind where I would have liked to have been at this point in the semester, but obviously things are quite different this semester. No big deal. There is a very short lecture on augmented reality, lecture 25, which I've moved to the end here. When we finish up virtual reality today, which we'll start in on lecture 26 on Cyborg Technology, which as you can see is a two-part lecture. I think our discussion of Cyborg Technology will take us through all of the last class on Thursday. If we finish lecture 27 early, we will move on and talk, we'll spend a little bit of time talking about augmented reality. Okay, if we don't get to lecture 25, it's not the end of the world. Okay, so back to virtual reality, where we are trying to increasingly immerse the human user in a virtual experience. And we started last time by looking at some of the physical context of virtual reality, trying to support the sensor motor feedback loops that we expect from the real world. We looked at some treadmills and some of the other systems that support the physical actions like walking, whole body turning, crouching, jumping, sitting, and so on. Then we switched and started to talk about head-mounted displays. How do you actually convince the human visual system that the human is observing a virtual world rather than the actual two plates of reflective glass that are very close to their eyes? And then we introduced the historical origins of virtual reality, which is deeply entwined with video games and computer games and goes all the way back to 1978 with the first text-based games. And I think it's important to remember that, of course, computer graphics has come a long way since 1978. We can do a lot of things visually and auditorially and even tactilely with a virtual reality system, but ultimately we are trying to create a virtual environment that relies mostly on human imagination. And obviously, fiction and writing have been doing this for thousands of years. Our species has experience with virtual reality over several millennia using older technologies like speech and storytelling and text. And only recently have we started to use technology to enhance that illusion. But ultimately, the aim is still the same. Okay, we ended last time by starting to look at, now that we actually start to have virtual reality, which is sufficiently accurate and fast enough to often convince or trick the user into thinking that they are actually in the virtual scene rather than in the physical world. Now that we have that technology, how and where do we use it? As always, we need to return to packed analysis. We need to think carefully about who is using the technology, what do they want to accomplish with it, and importantly, what are the physical and social contexts in which we are going to be deploying this technology. We looked at two recent applications or attempted applications for education. We looked at a nursing application. One of the challenges about training to be a nurse or any health professional is that you are not only becoming technically proficient in the health sciences, you also enter into a very intimate social compact with your patient. We looked at the case of mothers with young children who are struggling with substance abuse issues. So there are very difficult social contracts that need to be navigated in this situation. The nurse is physically present in the room with the mother and the child, possibly the doctor, possibly another family member. It's very difficult to train a nurse or to teach someone what that situation is going to be like unless you are actually in that situation. And so the immersive quality of virtual reality may be able to help allow nurses in training to dip their toes into that experience before they actually have to do so in reality. Okay. Another potential application for education is trying to scaffold or support spatial cognition. You probably all had the experience in biology class or even chemistry class, leafing through a very thick textbook. You're looking at the anatomy of an organism, and of course, if you're looking at a book, you're looking at a 2D cutaway of the organism. Organisms are not 2D, they're 3D. You need to rely on your spatial cognition to place together the slices of anatomy or the various vasculature and vasculature system, the neural system that you're looking at in a book of an organism, and try and imagine in your head how all those pieces fit together. Wouldn't it be nice if you could actually look at the 3D form, pull it apart into an exploded view, rotate it, perhaps enter into an anatomy lesson with an instructor where the instructor points at an object or manipulates it at the same time you reach out and also manipulate that part of the anatomy at the same time. Again, with any new technology, no one really knows what's going to work and what isn't, so we throw a whole bunch of things against the wall and see what sticks. Okay. So obviously there are a lot of emerging applications of virtual reality. This is an interesting figure that's taken from a review article on virtual reality in education. In a review article, or in this particular review article, they looked at a large number of other papers that were reporting results of virtual reality deployed into educational settings. And they were reviewing that literature, those large number of papers, to see what sorts of applications was VR being applied to, and what was working and what wasn't. In this first figure that I've extracted from the paper, they were looking at, they looked at 90 papers in total, and in those 90 papers there was some mention of applications or motivations. So where was VR applied and why was VR applied in to that particular education setting? So they drew out all those 90 papers, and then they did a keyword search, a relatively complex keyword search, looking for common themes across the paper. And they plotted this as the number of papers within the set of 90 papers that mentioned, for example, that simulation was a particularly important was an application of this. So they were simulating a particular situation or a social environment and trying to place the student into that simulation. You'll notice that I've copied this plot twice and rotated it 90 degrees. You'll remember our earlier discussion about information design. Not very happy with the way they did this. It's very difficult to read the legends here on the side. So we're going to skip back and forth between these two rotations of the same figure. So 41 papers out of the 90 reported that the application of VR in that educational setting, in that paper, had to do with simulation. Another 31 papers in this set reported that training was an important part of the educational, the application of VR to education in that situation. A large number of papers reported that VR was applied to an educational setting in which there was access-limited resources. So imagine you're trying to train a technician or a scientist to use a very expensive piece of equipment. Because it's expensive, there's only one at the university, or maybe there isn't even such an instrument at this university, there's one at the neighboring university. How do you take 30 trainees and get them all to collectively work and train on this instrument? If it's very expensive, it's hard to get access to it. Why not create a virtual version of that instrument and allow people to enter VR and train and interact with that instrument, train on that virtual instrument instead? It obviously makes sense. As we've all learned this past year, distance learning is a big challenge. There's ways to apply technology to distance learning. Some of those technologies work better than others, which again, we're all learning this year. If everyone's at home, and assuming everyone has a heads-up display, which we don't yet, maybe virtual reality is particularly useful for distance learning. I don't know about you, but it's sometimes challenging to teach and listen through a whole bunch of Zoom and Microsoft Teams meetings. It would be great if we could all meet in a virtual space and teach and learn together in that virtual space. Okay. Next thing they looked at in this set of 90 papers was motivations, the why of virtual reality. Why would you use it? One reason, obviously, is because it's a cool and emerging technology. As we talked about impact analysis, we want to think about what teachers and students want to do, want to accomplish in an educational setting, rather than focusing on what the technology could do. They broke motivations into pedagogical factors, which you can think of as the reasons why the instructor might want to use virtual reality for teaching something, and intrinsic factors, things that were intrinsically enjoyable or useful for the student. So this is sort of the motivations for the instructor, and these are motivations for the student. 4 different reasons why an instructor might want to use VR for education. The first one is constructivism. So what if you're trying to train your students to build or maintain something? Again, like access limited resources, it's very expensive and can be logistically challenging to set up a lab and have all the students come to the lab and build something and make something, especially if the materials from which they're building are expensive or access limited. Wouldn't it be great if we can all meet in a virtual space? I can show you how to build something or do something, and then you can do the same thing. What if we're trying to train students about a social enterprise? So again, going back to the example of nursing here, we might have the nurse and the doctor, or multiple nurses in an operating room. A group of medical professionals that are performing surgery need to work very closely together. They need to be able to maintain eye contact. Everything needs to go very quickly and efficiently. How do you communicate and coordinate and collaborate to execute the surgery as safely and quickly and as efficiently as possible? Obviously, the only way to do that is for everyone to be physically or virtually present in the same place at the same time. Okay, an instructor might also try and gamify what's being taught in order to increase student engagement, and there's other pedagogical or other educational reasons you might want to use VR. Okay, from the point of view of the student, why might a student want to use virtual reality? Well, of course, because it's more fun to learn something through VR than not. A lot of students who entered into testing of these various VR systems reported increased immersion. Again, especially this year when you're trying to learn at a distance, I imagine a lot of you often feel disconnected from me or the course material or what you're learning. That may be a feeling of literal distance for those of you that are not in Vermont anymore, but also an intellectual distance from the material. How do we reconnect with what we're trying to accomplish in the course? Well, one way is to try and literally trick your body into believing that you are in the classroom, you are with your other students learning something together, right? You remember that one of the most challenging non-functional requirements that we've talked about in this course is engagement. How do you make somebody feel that they're lost in the story, or they're lost in the virtual world, or they get lost in the unfolding material of a lecture or a course of instruction? A lot of students who use VR reported feeling more motivated to get up in the morning and go to class and put on the heads-up display or jump on the treadmill and actually enter into the educational experience. It's obviously more fun. The other nice thing about VR is we might all be in the same virtual environment, but that environment might be slightly different for each of us, right? We are not all looking at the same physical object. We all may be looking at slightly different variations of virtual objects. So much more easier to personalize instruction in a virtual environment than it would be in a physical lab setting or a physical classroom. Students reported deeper learning, that they extracted more material from the course using VR than they did without. Okay, again, VR is very new. Applying it to education is even newer. So there are a lot of studies out there that are looking at all the different attempts that are being deployed and trying to learn what works and what doesn't. Obviously, deploying any new interactive technology is always a challenge. In the same paper, the authors reported the various issues and limitations of virtual reality. In this case, among all the papers they looked at, there were only 35 papers that mentioned issue or issues or limitation and limitations. They were looking for these keywords. 35 papers had those keywords in it. They pulled out those 35 papers, and then they looked for common themes within those 35 papers. The first and most obvious issue and challenge is training and cost. So it's a bit of a challenge to get a Leap Motion for all of you for this class. I would love to be able to mail students next year a heads-up display and we do the class all over again in Oculus Rift. Probably not going to happen next year or the year after, right? Training and costs are still prohibitive. Then they distinguish between input and output problems. So input meaning input to the VR system. That could be input to the heads-up display or gloves. So input hardware usability. It was difficult for the user to figure out how to align or wear the heads-up display or put on the gloves and make sure that the gloves or the heads-up display was recognizing head motion or hand motion. Recognition inaccuracies. You all have firsthand experience with this, no pun intended. So the heads-up display may have a hard time detecting head motion or detecting gaze direction, where the eye is looking. We've talked about that already. If there are sensors in the gloves, it may be difficult for the sensors in the glove to infer the particular gesture being made with the hands in the same way that your Leap Motion plus your KNN has a hard time recognizing certain gestures. And also lack of feedback. So the system, the system is having a hard time picking up on whether the user detected that the system recognized something, and so on and so forth. So sort of this who said, she said situation, trying to set up this feedback loop where the VR system is projecting to the user and the user is projecting back to the VR system using head motion or eye motion or whole body motion. And are those two systems able to pick up on what the other is doing? Output problems. So these are problems from the point of view of the user themselves. So a lot of the users reported insufficient realism. Given what we've talked about in terms of heads-up displays and treadmills and maybe VR gloves that you wear, what might be going on that causes the user to lose, to sort of fall out of the illusion of the virtual experience? What are some of the things that break those expectations that the user has when they're interacting with a virtual reality system? What might cause someone to report, I used this system, but it didn't seem very real. I had problems. It didn't seem very real. There were things that weren't quite right. What might some of those things be? What are some of the remaining technological barriers that break that sense of immersion? There were a couple that were actually mentioned by people in the treadmill videos that we looked at last week. What are some of the most deeply entrenched expectations your brain has about head motion, eye motion, whole body motion? What sense feedback does your body expect when you move your head, move your eyes, move your body, that are particularly difficult for VR systems to support? Haven't seen anything in chat this morning. Hopefully you can still all hear me okay. So position and movement, yep, good point, Isaac. Remember, that's what the user is doing. But what's the sensory repercussion of change in body position or body movement that's often broken by VR, or is not quite perfectly supported by VR? So touch, yeah, exactly. Oh, other than footfall. So you might remember when we talked about some of the treadmills or the walking systems last time, people were walking in a concave bowl, and prediction about when you would feel touch or pressure on the soles of the foot wasn't perfectly supported by the system. Could be other aspects of touch that are not well supported by VR systems. And we're actually going to look at some tactile feedback systems when we get to wearables in a few minutes. If you've ever used a heads-up display, another big challenge is motion lag. When we move our heads, or when we move our eyes, we expect an immediate change in our visual scene. Takes a moment for a heads-up display to detect that our eyes have moved and to calculate how to change the projection onto the screens in the heads-up display to support that movement. If you don't get that quite right, a lot of people report motion sickness. And then the obvious culprit, as always, software usability. It's difficult to use the software supporting the VR system. Okay, some other challenges are that the VR system just simply wasn't useful for helping to teach or train the students in whatever they were trying to learn to do. It simply wasn't effective. There was a lack of engagement. That illusion wasn't created, and so on. Okay, so for those of you who are interested in how VR might be used in education, this is a great review paper to go and have a look at. So we're going to look at a couple of other aspects or features of virtuality. One of them that's kind of interesting is the legal implications of virtual reality. We've talked about pretty much every human domain in this course so far except for the law. I'm not a legal expert, so I will do my best to interpret here. This is an extract taken from a Masters of Law dissertation written in 2018. That was focused particularly on virtual property and insolvency. What happens if someone who owns virtual property in a virtual game passes away? Who owns that virtual property? The first question you need to answer in questions having to do with insolvency is, what is virtual property in the first place? How do you actually define virtual property? So Prinsloo here starts by describing some notable successes. So David Story here, way back in 2004, already invested $26,000 US in a virtual property in an unnamed computer game. Had sole ownership of all the island's hunting and mining rights. How would you enforce hunting and mining rights in a virtual property? Kind of interesting. Story was able to recoup all of his incurred expenses within a year of his initial investment, continues to enjoy monthly profit from it. Sounds like a well-managed piece of property. And as was pointed out here, this is virtual property. So how do you define virtual property? Prinsloo goes on to invoke the normal legal framework for physical property. And like many things in the law, it's very unlike science and engineering. There is no precise definition of what counts as property and what isn't. Instead, there are often a number of indicia or sort of features that you would expect to see with physical property and thus also with virtual property. Prinsloo focuses on 3 of these 5 indicia in his dissertation: rivalrousness, persistence, and interconnectedness. Let's start with rivalrousness. What does that mean? Well, it means that a system that is rivalrous usually can only be used or owned by one person at a time. There is a rivalry for possession or ownership or use in some way. Prinsloo illustrates this by contrasting virtual property with intellectual property. So intellectual property is intangible, like virtual property is, but it's non-rivalrous, meaning multiple people can use intellectual property at the same time, or have ownership over it, or have legal access to it, unlike virtual property. So you can limit the use of intellectual property through rights of exclusion, but that enforceable by law, but that's a separate issue here. Okay, so one person owns, uses, accesses at a time. right? If you buy a virtual axe in World of Warcraft, it's yours. Somebody else can't use it unless they steal it from you, you give it to them, you sell it to them, you trade it for something else. It's yours until you give it to someone else. Persistence. So a lot of the things in virtual environments come and go. Some are more persistent than others. Prinsloo gives the example from back in the day of video arcades and particularly Pac-Man. So you enter a video arcade and you play a good enough game that you're on the high scoreboard. No reasonable patron of a video game arcade would expect their name to stay on the top 10 list for long, as it's not unusual at an arcade for someone to reset or unplug. So people may be emotionally invested in the fact that they got on the high scoreboard at an arcade, but they don't have an expectation that it's going to be there for days or weeks or months or years. However, virtual property should be somewhat persistent. And again, this is a legal definition. It's not very precise. It doesn't say how long something has to persist to be considered virtual property. But your position or your score on the high scoreboard is not virtual property. It is something that could dissipate at any time at the whim of whoever owns the video arcade. So no reasonable person would expect their name to stay on the high scoreboard for any period of time. But George Costanza, a popular character from Seinfeld, was George Costanza is a lot of things, but reasonable is not one of them. It's one of my favorite Seinfeld episodes. George discovers that his high score, his high score from a Frogger game that was in a pizzeria when he was in high school. Not only is the pizzeria still there, not only is the Frogger console still there, but his score is still on the high scoreboard. Unfortunately, the pizzeria is shutting down and they're going to unplug the machine. So George Costanza hires a whole bunch of, hires some electricians to hotwire and plug in a battery so that he can get the Frogger out of the pizza and to his home. However, before he gets the Frogger machine back to his apartment, there's one remaining challenge that he has to solve.
Come on, George, I'll help you push it across.
Wait a minute. This looks familiar. This reminds me of something. I can do this.
By yourself?
Jerry, I've been preparing for this moment my entire life.
Looks like a frog. So do you.
Okay, so not perhaps as persistent as George would have hoped for. Okay, the last indicia that we're going to talk about today that that Prinsloo used to defend his definition of virtual property was interconnectedness, and this is the idea that virtual property has to be interconnected with something else. It can't exist in a vacuum. It needs to be interconnected with a large virtual environment that others participate in. And may be willing to buy or trade for that virtual property. It is the very fact that that virtual property is embedded or interconnected in a larger virtual ecosystem that gives that property value. If I open up a CAD system on my own laptop and spend hundreds of hours very carefully creating a virtual castle or a virtual property in my CAD system, that it has value perhaps to me, but isn't really considered virtual property from the point of view of the law, because it is not connected to other people, or it's not part of a virtual ecosystem. So like physical property or physical objects, different users must experience the virtual property in more or less the same way. So we're all inside of a virtual environment. We're all looking at the same virtual property. We might be seeing it from slightly different points of view, but we're all having more or less a similar experience of that virtual property. Okay, so we talked a little bit about education, a little bit about the law. Let's now talk a little bit about the economics of virtual reality. As we started this lecture, there is huge amounts of real, not virtual money to be made in virtual worlds. Here's an example from World of Warcraft, where there is something like a sovereign mint that controls how much money, or in the case of World of Warcraft, how much gold is generated and available for circulation. The gold is regulated very carefully according to supply and demand by the holding company or the company that owns World of Warcraft. As far as gameplay goes, gold is essentially created by an invisible source. Players cannot create their own gold and are not involved in the manufacture of gold coins. However, players can influence the economy of World of Warcraft. They can earn gold as quest rewards by mining for ore, pulling ore out of the environment and making it more easily circulatable among World of Warcraft players, or selling it for other items. One of the problems, however, initially in World of Warcraft is that you could spend real money, US dollars, to buy various objects or experiences or other things that would eventually translate into gold. So through a direct or indirect process, you could translate US dollars into gold. And then through other direct or indirect processes in World of Warcraft, you could convert gold back into US dollars. The moment you have this bi-directional translation between two different currencies, that creates a lot of ways for the bad guys to take advantage of that. Most of you have probably heard of gold farming. So enterprising people figured out that you could hire large numbers of people in developing countries and pay them less than minimum wage. So you pay them a small amount of currency to play World of Warcraft and grind within the virtual world to generate gold, which belongs to the person that's paying real money to these workers. You can then sell that gold. Sell that gold back to a user, or translate that gold back into much more US dollars. So a few years back, World of Warcraft introduced tokens, which was, among other things, an attempt to try and stop the translation of World of Warcraft gold back into US dollars. So currently in World of Warcraft, you can buy into the game and you can purchase one or more tokens, which you can then trade in. At the moment, one token in World of Warcraft gets you a little less than 300,000 gold in the game. Okay, a lot more we could say about the intricacies of economics in virtual games and some of the unique opportunities that such virtual economies open up for a black market. In the interest of time, we'll move on. The last application or feature of Henry says his old World of Warcraft account got hacked to be used for exactly one of these schemes. Exactly. So you can understand why World of Warcraft and other games companies are trying to suppress black markets in virtual economies. But like black markets in real economies, this is not a trivial thing to do. Okay. Again, we're going to switch gears now and look at another emerging application of virtual reality, which is for physical and mental rehabilitation. This is a recent article about this, but this is a process. This application has actually has been ongoing for a number of years. And what we're going to look at in this case here is TMT, trauma management therapy. So trauma management therapy is a form of exposure therapy using virtual reality technology. What is exposure therapy? We take a patient who is suffering from, in this case, PTSD or some form of anxiety, and we expose them to aspects of the stimuli that present or trigger that anxiety, and gradually expose them to more and more of that stimuli with the hope that they will habituate or acclimate to that stimulation. Okay. So in this paper, they contrast TMT, which is using VR for exposure therapy, to traditional exposure therapy, and they contrast it. So it does, both systems use the construction of an imaginal scene, where we're going to construct this. We're going to gradually build up the realism of the scene to recreate the traumatic stimuli or the traumatic event. Unlike traditional prolonged exposure, which is usually administered in fixed chunks because someone needs to come into the lab or needs to come in for a session and it's fixed. Exposure therapy in TMT continues until within sessions habituation, so meaning that habituation or the anxiety starts to decrease within the session, during the session. So the exposure continues until habituation is achieved. Therefore, within the VR system, exposure therapy sessions may be very long to begin with. The initial sessions of any exposure therapy, for those that have ever done this, or as you can probably imagine, are particularly difficult for the patient or the subject. They might last for a very long time because we supply in VR a very small bit of the upsetting stimuli. However, by dynamically tuning the realism of the virtual experience, so it's just on the edge of anxiety, it makes it easier for someone to habituate. It's very easy in exposure therapy to present too much of the stimuli or too little. We're going to more easily modulate the amount of stimulus using virtual reality. So at the beginning, very long traumatic sessions. Towards the end, they're very short. And overall, they found it was easier to work with the patient for them to completely habituate to the stimuli using virtual reality than without. In this study, the virtual reality exposure therapy used the virtual Iraq of Afghanistan system. So they were working with PTSD warfighters coming back from various theaters of war, whereas you can see from the images here, the virtual reality scene was meant to try and transport the veteran back to the traumatic event. The system is customizable using a Wizard of Oz interface. So we talked about Wizard of Oz interfaces at the beginning of the course. So there is a therapist on the other side of the system who is actually pressing the buttons and increasing and decreasing the visual, auditory, olfactory, and/or tactile sensations in the event. So as you can see, this is a very multimodal system, meaning that it's designed to present stimuli to different sense modalities: eyes, ears, nose, the tactile system, your vestibular system. Elements are delivered via a head-mounted display, earphones, and a scent machine for the olfactory part, and a rumble platform. So especially for veterans, we need to create the illusion that they're moving in an armored vehicle or they're moving through the environment. In this investigation, the virtual environment was customized to the individual patient's traumatic scene. This is another advantage of VR over traditional rehabilitation systems. It's much easier to customize the system or customize the amount of reality needed to get to the edge of habituation. For example, if during the imaginal scene the participant said, "and then I smell diesel fuel," so they are mentally recounting a traumatic event in this session, the therapist would deliver diesel fuel or the scent of diesel fuel utilizing a scent machine driven by an air compressor. So you can imagine there's some significant hardware and software challenges to such a system. Okay, so to finish our lecture on virtual reality, just a quick couple-minute in-class exercise here. Let's imagine that you've been tasked to run a completely virtual robotics conference. So as you can imagine, this past year, all the academic conferences that used to be held in person were all held remotely. I was the organizer of a conference this past summer where we had 350 participants. And most of the participants were roboticists. It was very difficult to recreate the common experience at a conference. Because the reason everybody travels to an academic conference is to try and do things or learn things from one another that would be difficult to do by writing papers or recording YouTube videos for each other. So how could we try and bring back some of the advantages of physically meeting at an academic conference when we can't actually meet in person? So just to give you an example of what goes on at these kinds of academic conferences, there's the traditional holding a lecture. People come to the lecture and ask questions. That part, obviously, we can usually supplant relatively easily with a Zoom call and chat, real-time chat, and so on. Much more difficult to do a remote workshop. Workshops are meant to be much more interactive. People are arguing and demonstrating technologies or arguing about certain points. There's a lot of complex social interactions going on within a workshop. Presenting posters is also obviously difficult. If you're a junior member of the academy or a new student or you're just starting out, you might present a poster, which is the beginnings of an idea. You stand by your poster and various people at the conference come by, they look at your poster, you ask them if they'd like an explanation of the poster, you explain different parts of the poster, they stop you mid-sentence and ask about this figure. Some other people stop by and they look over the shoulder of the person you're talking to. Certain social dynamics that go on around a poster presentation that are hard to recreate in a remote setting. And finally, just informal social events. So how might you use the various VR technologies we've talked about or other ones to support some of these sort of hands-on or more interactive aspects of the conference? So imagine we have a workshop where people are going to come together and build simple robots or do some simple things together. So it's a workshop that's sort of a mixture of demonstration and teaching. How might you deal with accessibility issues? So if this is a robotics conference, there may be certain people that are attending the conference that are coming from well-funded robotics labs, and there are VR headsets lying around, leap motion devices. But there may be other people that are attending the conference that have none of that, let alone a good internet connection. How do we level the playing field for these diverse participants in the conference? And finally, and as always, how do we deal with some of the more subjective sides of a conference, like the social aspects? So one of the most difficult things for new students is that when they go to a conference, it's very intimidating. They don't know anyone. How do we involve junior members of the academy, people that are just starting out as grad students, and how do we draw them into in my case, how do we draw them into the robotics community? I'll give you a few minutes to think about that. I've numbered these Q1, Q2, Q3. So if you have an idea, you can type in R1, R2, or R3, which is your response to one of these three questions. Okay, I'll give you a couple minutes to think about that. When you're ready, just go ahead and type in any ideas or responses in chat. Okay, some really great ideas coming through on chat here. In response to Joseph's point, different robots definitely do have different smells. I like that idea. Common theme here is breakout rooms, and this is something that we did try at the conference this past summer, which is we created small breakout rooms which were students only, no professors allowed, which again created a bit more of an informal setting, and I think a lot of students felt a little bit more emboldened to present ideas than they might have if they could see that there was a famous robotics professor in the room, or there was the threat that a professor might walk into the room. So a lot of good ideas here. Good ideas about accessibility here. So those that have VR headsets can walk around and demonstrate, but make sure that it's recorded or presented on YouTube or live streamed in some way for those that can't participate in real time. Yep, VR Minecraft, that's a great idea. I think actually someone at our conference did set up a Minecraft server, and I think some of the students later at night did participate. So Minecraft is indeed the solution to everything. Okay, so that's virtual reality. We're going to switch gears now and talk instead about looking inward from the opposite direction. Wearable technologies and cyborg technologies. So we'll start, we're going to organize these two-part lectures, again, by moving inward. So we'll start by wearable technologies, which are obviously worn on the skin. The moment you're thinking about hardware and software that is in contact with the outside surface of the human body, there are very important or unique physical context that informs how you go about designing that technology. I'll play this video in a moment, but even just looking at the screenshot from this video, you can probably start to guess about what some of this physical context is. If you have an idea, go ahead and type it into chat. The Leap Motion device is a great interactive technology. It's able to detect various grasps of the hand, but one of the things that it can't help with is object manipulation. How do we augment or support gripping or grasping or manipulating of objects? What are some of the physical challenges or physical opportunities that arise when you have electronics or technology that is directly in contact or almost directly in contact with human skin? Let's think about some of the physical challenges first. What are some of the things that you better get right if you're going to create technology that is in physical contact with the human body? That may be less important. That may be less important if it's the Leap Motion device. It's not something that's in contact with the human body. What physical context is most relevant here? Unfortunately, Minecraft can't help us here. Maybe it can. Absolutely. So there's physical safety here. It has to somehow not be painful. No exposed circuitry. Yep, no electrocution. No poison, heat. Apparent temperature for touch. Yeah, so obviously the skin, assuming that the glove or the intermediate material allows diffusion of heat or cold through. How does it feel on the skin? Remember our discussion about ubiquitous technology. We would like ubiquitous technology, which includes wearable technology, to disappear into the background. In theory, in virtual reality or wearables, we would like to eventually lose ourselves in the illusion, not even be aware that we're wearing anything at all. How do you need to design the hardware to help wearable technology disappear into the background? So not too heavy, and it shouldn't constrain motion. So let's focus on the constraint of motion. Most technology that you're familiar with, your smartphone, your mouse, your Leap motion device, your laptop, your desktop, they're all rigid technology, right? They're not flexible. One of the biggest challenges in wearable technology, at least from the hardware side, is flexibility.
This ultralight glove was jointly developed by the EPFL and the ETH in Zurich. It was designed to allow users to grasp and feel virtual objects with a high degree of realism, so the user can really feel an object that doesn't exist. Unlike existing solutions that are typically based on large exoskeletons or bulky fluidics or thick cables, our solution is extremely lightweight and portable. The glove over here, it weighs only 8 grams and is 2 millimeters thick. It requires only 200 volts and a few milliwatts, which means we could easily miniaturize the electronics and add a small battery to have a fully portable solution, allowing users to be completely free when they manipulate objects in virtual reality. In the virtual environment, when the user is about to make contact with an object, the glove blocks the finger's motions, and that gives a highly realistic sensation of actually touching a real object. So the way it works is that we have 2 metal strips on each finger, and they normally can slide very easily, allowing the fingers just to move very naturally without blocking the motion. However, as soon as we apply voltage between the strips, in a few milliseconds, they're blocked together, and that prevents the user from then closing his hand. We have up to 40 newtons of force per finger, and that means we can generate sensations of holding a very, very hard coffee cup, but also something soft like a sponge. The system was tested by our partners in Zurich on several volunteers. They were asked to perform virtual reality manipulation and grasping tasks that required a high level of precision. The results were extremely promising. Users reported feeling very accurate sensations of touching objects and were very accurate in the tasks they were assigned. With further improvements, we plan to develop eventually a complete suite for virtual reality environments.
Okay, so as Matthew mentioned, we don't want to constrain motion, but in some cases we might dynamically want to temporarily constrain motion to give the illusion that the user is grasping a virtual object. So obviously if you're grasping an object at a certain point, that object constrains further constriction or further closing of the hand, and they do that using these metal strips on the outside. They mentioned that they can simulate the grasping of hard and soft objects, which you could imagine takes a fair bit of machine learning. How do you actually constrain the fingers to give the illusion that you're grasping a soft object versus a hard object? Lots of interesting machine learning applications there as well. Okay, so here we have some flexible metal strips that don't constrain motion when the user is not grasping a virtual object. One of the challenges in wearables is that we need to try and make all aspects of the system soft. One of the aspects of technology that's particularly difficult to soften is electronics. You'll notice that right at the end of the video here, they were 3D printing wires into a mesh or a net that is covering the surface Why? Why print a net of wires? What are they trying to capture? What function are they trying to capture using this? Sorry. What are they trying to capture with this spider web of stretchable wires embedded in this flexible material? Why not have all the wires bunched up in one part of the material and leave the rest of the material free? As Joseph mentions, as they mentioned in the video, because the resistance changes depending on how it's stretched. So the stretching of the flexible wires changes resistance, and the change in resistance is the input to this interactive device. That is the sensor. It's trying to detect how this fabric is deforming over time, which is a hint about how the user is moving their body. So using a wearable device, you could relatively easily, with this technology, have a real-time picture of the kinesthetic state, what is the orientation of all the body parts in space, right? So capturing or inferring whole body motion is particularly difficult in a virtual reality system unless you have a series of distant cameras. It would be great if you could record body motion at the body. Okay. We're going to look at another example of this wearable technology. Again, going back to rehabilitation in this case. This is the Locomot system developed in Switzerland, and it's now deployed at several hospitals throughout Switzerland. It is, again, a therapy device, but in this case, not emotional therapy like we just saw in the case of the PTSD sufferers. In this case, this is physical therapy. It's used mostly for patients that have suffered spinal damage and have lost control of their legs, but there is a likelihood that they may be able to recover lower body movement. One of the biggest challenges about recovering lower body movement after a spinal injury is a chicken and the egg problem. Why is it chicken and the egg? The spinal cord and the brain learns how to walk or relearns how to walk after injury by recognizing the motions of walking. Remember our discussion that recognition is often easier than recall. It's very hard if you haven't walked for a long time for your brain to remember how to do it. You can forget how to walk. But if the brain needs to be reminded about walking and it can't produce walking, how does the brain get the relevant sensory stimulation of familiar walking? There's a chicken and the egg problem. So the Locomot system, and I'll just start the video here and talk over it. The Locomot system, as you can see, and maybe I'll speed this up, it's a little bit longer video. The Locomot system is a wearable exoskeleton, as you can see in the bottom right picture. We're going to allow the patient to wear this exoskeleton, and the exoskeleton is then going to drive the motion of the patient's legs. So the Locomot is going to walk the human patient, which generates the relevant sensory stimulation in the lower part of the body, which is collected by the healing spinal cord, and provides the right sensory stimulation for the spinal cord to gradually start to send motor commands to the legs again to try and generate walking. That's phase one. What do you think happens in phase two of physical therapy with the Locomot device? In phase one, the Locomot walks you. In phase two, you walk the Locomot. So the Locomot system is generating walking, but it also has sensors on board to record how much force is being generated by the user's legs. So is the user's legs purely passive? The Locomot knows how much work it needs to do. The moment the Locomot detects that the user is contributing something to the walking effort, it will slowly decrease the force of the motors until at the end of training, the Locomot's motors are completely turned off, and it's acting as a passive wearable device. It's actually not doing anything. This is yet another form of a phenomenon we've talked about many times now throughout this course. What is that phenomenon? Exactly, yet another example of scaffolding. Okay, here's another example, very similar. This is again a physical therapeutic device. This one is meant not for those that have suffered a spinal cord injury, but for those that are recovering from a stroke. In the unfortunate case that you suffer a stroke, one of the biggest challenges after the fact is muscle synergies. One of the hardest things for your brain to do is to be able to control different muscle groups independently. I can flex my index finger without flexing my other fingers. If you watch any videos of young children, they very rarely do this. They do this because they have not learned how to break muscle synergies yet. They haven't figured out, if you think of the brain as controlling the strings of a puppet, as a marionette, very difficult to control the motion of one muscle group while leaving the other ones intact. A stroke can break or disrupt the brain's ability to do so. So the particular therapeutic device we're going to look at now is designed to try and reduce these muscle synergies. How does it do that? It allows the patient to initiate movement, as you'll see in the video in a moment. So the patient is in control at all times, but is assisted. So this is an assisted device. And the device is designed to allow the patient to focus training on a specific muscle group. So one of the hardest things for a stroke patient is to try and flex the bicep, but not raise their shoulder, at least in this particular case. This is a year and a half after this particular patient has suffered a stroke. You'll notice that they're flexing their bicep, but also raising their shoulder. So you can see the synergy here. So in this case, the orthosis that they're wearing is applying forces and actually actively resisting the contraction of certain muscle groups. So it is trying to hold one part of the patient's arm still while allowing the patient to flex or rotate the lower part of their arm. So the device is actively breaking the synergy for the patient while the patient is flexing. So not that different from the Locomot. So after 16 sessions of training, you can see she's flexing her bicep again. Her shoulder is still rising a little bit, but not as much as before. So the synergies are significantly decreased here. A little more than a year after she first started working with this device, and the synergy is almost gone, and she's been able to keep the reduced synergy even after not using the device for a significant period of time. Okay, so you can imagine a lot of therapeutic applications of wearable technologies. We are now going to switch from talking about wearables to cyborg technologies. Where does the word cyborg come from? Well, it dates all the way back to the 1940s and earlier, to the study of cybernetics. Cybernetics was an offshoot of electrical engineering, and the focus in cybernetics was to create electrical devices that performed some function based on feedback. So very simple examples of this. You have a thermostat that detects temperature in the room. If the room is too cold, it'll turn on the heat, so the heat will raise the temperature, which will then shut off the device. And we have a very simple feedback loop between a thermometer and a heating element, which gives you a thermostat. That's a simplest example of a cybernetic device. These were of great interest in the early 30s and 40s. One of the founders of the field of cybernetics, Norbert Wiener, is seen as not only the father of cybernetics, but also the parent of the child disciplines that grew out of cybernetics: artificial intelligence and robotics. Both AI and robotics don't have this concept of feedback as clearly obvious in them as it was in cybernetics, but it's there. As we've seen many times now throughout this course, there is an important feedback loop in both machine learning algorithms and in robots that provides the ability for an AI or a robot to start to learn. So cybernetics, again, is this idea. We've dropped the netics. Obviously, we all know about cyber. This is where it comes from. Way back in the 1940s, Wiener not only envisioned these completely artificial feedback loops like a thermostat that had no direct contact with humans. He envisioned nervous prostheses, as he called it, cybernetic devices that were part of the nervous system of a human being. He recognized that in a human being there are already feedback loops, right? I act or push against the world and I observe how the world pushes back. But part of that feedback loop goes from my eyes, for example, if we're talking about the visual sense, from my eyes to the optic nerve to visual cortex, which is at the back of the brain. That's one part of the feedback loop. That pathway may become damaged through injury or developmental defects. There is another part of the outward part of the feedback loop going from motor cortex, which is sort of the strip of your brain that if you were to wear Bose headphones, that's the motor strip. Those are where ideas about how to move emanate, and they flow outward from the brain to the spinal cord, to my hand, and out to motion. So we have this whole feedback loop that goes to the environment, back to a sense organ like the eyes, to the optic nerve, to the brain, from the brain to the motor strip, from the motor strip to the spinal cord, from the spinal cord to the hand or the leg or the whole body. Could we create cybernetic devices that implanted in the body would supplant or support that feedback loop, that part of the feedback loop that goes from brain to muscles or from sense organs to the brain if they're damaged? So this is an idea of bypassing part of an already existing feedback loop that has become disrupted. Okay, so let's go back to our common cartoon here where we have a user that's interacting with the computer or the physical world or the social world. Up till now, we've been assuming that the user, the human participant in this feedback loop, is one monolithic whole. We're going to take the human and explode them into three different parts: the brain, our muscles, and our sense organs. And as I mentioned, we're going to start next time talking about cybernetic devices that mediate or that capture signals from the sense organs, from the eyes, and bypass, for example, the optic nerve, which connects the eyes to the brain. If the optic nerve becomes damaged, it's the cybernetic device that supplies data from the eyes to the brain. If our spinal cord becomes damaged and the brain cannot send signals to the muscles, can we surgically implant a cybernetic device that collects motor imagery, ideas about how we would like to move, and supply those signals directly to the muscles? Okay, so we now have a very different picture of a human-computer interaction loop. We'll stop there. You have a quiz due tonight. You're working on Interim Video 3, and we will talk about the final project deliverables Thursday morning. Have a good rest of your day, everyone. Thanks very much. Bye-bye.